Hey, Chem 11. So going over some of the answers from the worksheet for lesson 1. The first question 1 is a table of number of different isotopes, and you're asked to fill in information about those isotopes, especially mass number, atomic mass, number of protons, and so forth. This is really about understanding what it means for there to be two isotopes of a given element. And a reminder, two isotopes of a given element are going to be particles that are identical in the number of protons, but different in the number of neutrons, making them different isotopes with different atomic masses. Now, to fill in this table, we see, I'll just zero in on it for a moment here. Our columns are isotope name, atomic number, mass number, standard atomic notation, number of protons, and number of neutrons. The mass behind this is really quite simple. For the atomic number, that will always be exactly equal to the number of protons. And if you know the atomic number, then you know what the element is. In this case here, atomic number 6 is carbon. The mass number is the mass of the nucleus, measured in units, at least for whole numbers, of neutrons and protons. Neutrons plus protons gives you overall atomic mass. Because neutrons and protons have about the same mass, you can just add them together to get the total mass. So for carbon 14, well, the name for the isotope can be shown as element name dash 14, which is the mass. That's one way of writing out the name for that isotope. It has an atomic number of 6, mass number of 14, which is just the mass, and then 6 protons and 8 neutrons. This here, the standard atomic notation, you should be familiar with that, where it is shown as an element symbol. To the top left of it is the atomic mass. Bottom left is going to be the atomic number, which will always be the same. Sometimes this number here, that 6 in this case, will be absent because after all, if it's carbon, it's going to have a mass number of, an atomic number of 6. Oxygen 16, atomic number 8. You can get this from the periodic table. Mass number 16, you know that because that's right here. The symbol O16-8. Oxygen, mass 16, number 8, 8 protons and 8 neutrons. Now, you'll have noticed, I'm sure, that if you look in the periodic table, the masses are very often not whole numbers. You know, often it's going to say something 0.0, like 39.0 for, argon? I can't remember. It'll give you these whole numbers. That's very common, but you're often going to see a decimal after. This is because natural samples of any given element will be a mixture of isotopes. You can separate them. There's technology for doing that, but they're not normally going to be separated. If there's more than one possible isotope, whatever sample you have of that pure element will have some of one and some of another, but not necessarily in equal amounts. Some isotopes are much more common than other isotopes. There are elements that have effectively only one isotope that you'll ever find, and all other isotopes are unstable, so they won't be found in nature. Those are the ones that are going to be like such and such 0.0. But then there are other elements that have several isotopes. Tin has 20-something isotopes. It's a very large number that you find for some elements and not others. Here, it's a matter of, okay, well, what's the atomic mass that you report in the periodic table? The atomic mass is an average of those atomic masses of the individual isotopes, where each one is weighted by the abundance. How do you do this? Well, if you're told that in natural samples of, say, boron, 18.8 of those percent of those natural samples is boron 10, and 81.2 is boron 11, you get the atomic mass, which would go into the table of 0.188, that's your 18.8%, times the 10, plus 0.812, that's your 81.2%, times 11. And that'll give you this right here. Hey, by the way, notice what I put in here? Units are important. The unit here is the atomic mass unit, but that corresponds directly to molar mass. So we can say that the atomic mass is 10.8 AMU, the average atomic mass. But the molar mass, which you can get from that directly, is 10.8 grams per mole. That's how you do those problems. Any of these problems you're given, you're just taking these percentages, converting them to decimals, multiplying them by the associated mass number that you were given for that isotope, and adding it all up, and that'll always give you the correct answer for that. So those are all the questions that I'm going to review up on the board for lesson 1, and the rest of it I'm hoping you can get by your viewing of the screen lesson. Chemistry 11. So this is going to be your screen recording lesson for the lesson 1 of Unit 8, the atoms in the periodic table. You know, some of this you'll have seen before, some of it you won't have seen before. Bottom line, I'm going through quite a lot of material at once here with it trying to focus on some of the skills. So a little bit about history of the atom first. Obviously, it hasn't always been known that all matter is made of atoms. It's a very old idea. It actually dates back to ancient Greece. Democritus had this idea of the atomos, that which could not be cut any further. The idea that you could only split any sample of any kind of matter to a certain point and then no further. And that's where the term atom comes from, uncuttable. Now, it was just an idea, and it was really, at that point in time, when it came to evidence, no more valid than idea that there were 4 elements that all matter was made of, which comes from Aristotle. So the Greeks were big on ideas, but not quite so much on evidence. It took more modern chemistry to start getting a better understanding of atoms, which of course has developed over time. We start with John Dalton in the early 1800s. He had this idea that, yes, all matter is made of atoms, but he didn't know about subatomic particles. He just figured, well, different atoms correspond to different chemical elements, but that the different sizes of those as balls, the spheres, corresponded to the different elements, and that they could be joined in different ratios and in different ways to make different compounds. You know, a lot of the fundamental ideas that we do understand as part of modern chemistry, John Dalton had these as ideas, but some of an understanding of what went on within an atom was not part of his theory. Further developments, though, in J.J. Thomson was the one to discover electrons. So we had this idea that the atom had an overall positive charge, and within it, called the plum pudding model, there were electrons floating within, so that atoms were actually made of a balance of positive and negative charges. That kind of dates to him, and he came up with some of the evidence to support that. Some of the biggest developments, though, really came shortly after that from a guy named Ernest Rutherford, because what he did is he established that, yes, atoms are very small, but the nucleus of an atom, where most of the mass is ridiculously much, much smaller. There's a great video on this, a TED Ed video we would watch if you were in class, called How Big is an Atom? You might want to give that a look. What he did to come up with the evidence behind this was his famous gold foil experiment. He was using alpha particles, which are really just nuclei of helium atoms, something he also figured out, and he was bombarding gold foil with them. And what he found was that some of the alpha particles, when bombarding this very thin layer of gold foil being far, far thinner even than paper, most of them would go through, showing that most of the atom was empty space, but a few of them would fire right back and hit a screen that was basically the same direction that the alpha particles came from. In his gold foil experiment, what he had done was show that most of the atom was empty space, but he concluded as well that there was a very small but incredibly dense part of the atom in the middle and called this the nucleus. He concluded that it had a positive charge and that the electrons, which there was evidence for, were orbiting the nucleus and occupying most of the space. So this was, of course, a huge development in understanding atomic chemistry with Ernest Rutherford. Shortly after Ernest Rutherford, though, we have Niels Bohr, and it's really the Bohr models that are pretty much where high school chemistry, I wouldn't say it stops, but much of the understanding that you need for the unit on the atom in the periodic table can draw on Niels Bohr's findings that the electrons are not allowed to occupy just any old space around the atom. The idea that they should is a bit counterintuitive, because you might that they could just be anywhere is a bit counterintuitive, because you might ask yourself, well, why don't they all just collapse downwards towards the nucleus? The planetary model of Niels Bohr, or the model with shells, it proposes that electrons orbit the nucleus in predetermined electron shells, that they're not able to occupy any other spaces other than those shells. This is based on evidence of what happens when you bombard samples of an atom or of an element with high energy electromagnetic radiation. It's found that it re-radiates that back at you, but which is what's expected, but that it does so at certain set wavelengths. The conclusion being made is that the electrons, when they're bombarded with, when the atoms are bombarded with electromagnetic radiation, they gain energy, they hop up some energy levels, and then they go back down. But when they re-emit that electromagnetic radiation, it's only at certain it's only at certain units of energy, certain quanta of energy. His conclusion was those quanta of energy corresponded to the energy differences between electrons in the different shells. We're going to get more into shells in later lessons, but just going forward one step to the quantum model, which is really what we have today, this notion of the electron as being its own particle which occupies any particular point in space is what then had to be discarded of. The more modern understanding views the electron as as an object that has some of the properties of a particle, a mass, for example, but then some particle properties of a wave, as is light, a wave. Now, of course, a wave, and only a wave, like light, has no mass. So the electron has the mass property. It's called the wave-particle duality, where the electron has some of the properties of a particle, like mass, but also some of the properties of a wave, and that the electrons orbiting a nucleus do so as what are called standing waves orbiting the nucleus. So that's where I want your understanding to be for the history of the atom theories and models. What was done by experimental chemists over really the decades is that they began to discover that, yes, there were certain chemical elements, substances that could not be broken down into simpler substances. And particularly a man named Dmitry Mendeleev, started to organize these elements by their chemical properties. And he realized that there were certain patterns that were repeated within the periodic table. Well, of course, he didn't know it as a periodic table back then, because he helped to develop it. He helped develop it by arranging the elements and seeing that there were repeated patterns in their properties. The understanding of, they had oxygen, for example, that was a known element. Sulfur was a known element. Carbon and silicon were both known elements at the time. And he was finding that, oh yeah, oxygen and sulfur have similar chemical properties. So do carbon and silicon, and so forth. He knew a large variety of these chemical elements, including their chemical and physical properties, and found these patterns of repeated properties within the periodic table. which led him to build a table that looks more or less like the one you see here. So some of those properties include reactivity, chemical reactivity. The most commonly referred to elements when we're talking about different columns in the periodic table are alkali metals and halogens. But you know what, actually I should back up and say, here are some key points for you to know. Within the periodic table, the rows are called periods. Okay, so this is period 1, hydrogen's period 1, so is helium. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon are the period 2 elements. Here are the period 3 elements. It's very simple. The rows are the periods in the table, and the columns are also called groups, or sometimes called families. It's with these groups and families that we see these repeated chemical properties. The finding that hydrogen, lithium, well, particularly lithium, sodium, and potassium have similar chemical properties, as well as, we see here with what are called the halogens, fluorine, chlorine, bromine, and iodine are the halogens, and they have similar chemical properties. And right next to them in the periodic table, we see as well the noble gases have these repeated chemical properties, similar chemical properties to each other. Not identical, but similar. If you look at the alkali metals, this is a video I found that shows the different alkali metals reacting with water. What is shown in the video is that alkali metals are similar in that they're all fairly soft enough that you can cut them with a knife. But otherwise, properties of metals, they're malleable, they're conductive. But another property of alkali metals is their reactivity with nonmetals. Of course, water, H2O, contains nonmetals, so not surprisingly, alkali metals are very reactive with water. So I believe what he'll have here, I brought the sound off, but he'll probably have lithium, and then here he's going to add sodium to water. A bit more of a powerful reaction there when you're adding sodium to water, and then adding potassium to water, even a far more powerful reaction. But in the case of all of them, this is what you see, is that they react powerfully with nonmetals. So that's your alkali metals, that's the trend with them. There are other patterns and trends from the periodic table. One of them is the high reactivity of the halogens. The most reactive chemical element of all, at least the most reactive nonmetal, is fluorine. Here's an example of a reaction involving fluorine. All that's being done there is they have a tube right here. The tube is actually lined with nickel fluoride. There's not much that fluorine won't react with, but if you line a tube for a vessel that contains it with a fluorine compound, then the fluorine won't react with the tube any further. That's the only way you can store it, because you can't store it in glass. When the fluorine is just puffed into the air against steel wool, we see what happens. This reaction might look to you like burning steel wool, but that's not burning steel wool. All that's happening is room temperature fluorine is being puffed against the steel wool and causing a reaction. Steel wool is mostly iron. The fluorine is of course a chemical element. So mostly what we're making here would be iron fluoride. The one thing I also wanted to mention is that there is a trend in reactivity across the table that extends beyond the alkali metals. As we go from the alkali metals, powerfully reactive in water, we find that the next column over, column 2, is the alkaline earth metals. The alkaline earth metals are similar to the alkali metals, but, well, not really quite so dramatic. Beryllium, magnesium, calcium, strontium, barium. These are alkaline earth metals. Each of them is got one more proton and therefore one more electron than its neighboring alkali metal. And you find that whereas in the reaction here, where we added potassium to water, there was an explosion. Calcium right next to it, if we add that to water, yes, it reacts powerfully, but no beaker is being blown up here. Another pattern I want to talk about a little bit within the periodic table would be patterns that work from vertically within the columns. Here are some elements known as the chalcogens. Here they are within the periodic table. This is column or group 16, oxygen, sulfur, selenium, tellurium, and polonium. Notice that they kind of bridge the nonmetals with the metals. Oxygen, of course, is a nonmetal, as are all of these elements here in green, as well as the noble gases are all nonmetals. These are the ones in green are nonmetals and reactive. Oxygen, sulfur, selenium, and tellurium, they are two different states and include nonmetals. Tellurium, which is a semi-metal, I should call it a semiconductor, because that's what it's called in your notes. Tellurium, and polonium, which is a metal called a post-transition metal. Let's look at them. These are all within the same group. So a moment ago I talked to you about alkali metals and showed you how they really are very similar to each other, although there was kind of a hint that when we react, we put lithium in water, it was pretty reactive but not explosively. Sodium was more dramatic. Potassium was particularly dramatic. It's by the time you get down to rubidium and cesium and francium that you get the most explosive reactions. So that reactivity increases, but they're all soft metals that react with nonmetals. If we look right here, we expect, all right, well, these are really similar. Won't these be? Yes, they are similar chemically to each other, but they're hardly identical. Oxygen, of course, at room temperature and pressure is a gas. Sulfur is this yellow solid. Selenium is a crumbly, brittle solid, looks slightly metallic. Tellurium is a semiconductor, looks much more metallic. And then polonium, well, we can't really image polonium very well because it's so very radioactive, but polonium is definitely a metal. So the overall conclusion that can be made from this is that what's called the similarity to metals or metallicity increases as you go down the periodic table. We see it here as well. Fluorine is a pale yellow gas. Chlorine is a pale green gas. Bromine is more of a brown liquid. Iodine at room temperature is a crystalline solid, and acetine is too radioactive for us to know. So we're going from a gas through to a liquid to a solid within the halogens. That's increasing metallicity. We see it, in other words, across the periodic table. As you go down, the similarity to metals increases. And also, the more obvious pattern is that as you go from right to left, the metallicity increases. Hardly surprising. These are the nonmetals right here, and metals are towards the left side of the table. By the way, there's an important group of elements here, which are really, well, the bulk of the elements. The bulk of the elements, most elements are metals, and you've mostly never heard of them. You've heard of carbon, I'm sure, and oxygen, but you probably have never heard of scandium until this course. You probably had never thought about ruthenium or osmium or hafnium. These are all chemical elements, but they're not well known. What they are called is transition elements. A reminder, by the way, that you can get all kinds of information from these tables right here. For reading a periodic table, we see that scandium is 21 with 21 protons. Symbol is Sc, and the atomic mass is about 45. So most of it will be scandium 45, although it looks like there's some other isotopes there. Anyways, got off on a bit of a tangent there. The other thing I want to mention is atomic radii, patterns of atomic radii. So it's a little bit counterintuitive, really. The atomic radius is just what it sounds like. It's what is the radius of the atom. In this case here, we treat the atoms as balls. What is the radius of each? And we see a pattern that you might not expect, because you might think, well, if these atoms here of increasing atomic mass are bigger, surely the atoms involved are going to be get bigger as we go by atomic mass increasing. But what you find is exactly the opposite. We find that the trend across a period is for the radius of the atom to decrease, not to increase. What's happening here will, I think, become a lot more clear when it comes to lesson 2. But I will tell you this, that atoms include positive and negative charges, that negative charges and positive charges are attracted to each other. The negative charges are held by electrons, the positive ones are held by protons, and the atom is held together by that mutual attraction of positive and negative charges. That as we increase an atomic number, say from sodium to magnesium to aluminum to silicon, the number of protons in the nucleus is increasing. We've got more protons to attract the electrons. With a stronger force of attraction, the electrons are pulled in more powerfully by the larger nucleus. Most of an atom is empty space. So the actual size of the nucleus itself should not be expected to have a very great effect on the size of the atom in as a whole. That's all for the lesson on the atom and the periodic table. I hope you find it useful. The next lesson I will be posting will be lesson 2, electron configurations.